Oh, hello. Didn't see you there. If you're interested in engineering, this video will be right for you. Today we're going to take a look into fluid mechanics. Come on, y'all. Let's go force ourselves to solve this problem. Engineers use math and logic to solve problems for everyday life. Without engineers, we wouldn't have computers, cell phones, or even cars. Fluid mechanics is an important subject for different kinds of engineers, such as mechanical, aerospace, and especially chemical engineers. A fluid is anything that flows, like water. Fluid mechanics is studying the physics of these fluids, such as liquids and gases. Using fluid mechanics, engineers can analyze everyday objects, such as a simple glass of water. We're going to do a fun experiment on this glass of water. If you don't understand the math, don't worry. Just try to make the learning fun. If you think about it, there's all kinds of forces acting on this cup. Gravity is pulling the water down, the water is creating pressure along the walls, the motion of the water molecules gives it a certain internal energy. I can go on and on. But if I move the cup along a surface, I'm giving it a force, and I can use equations to solve for the acceleration. I can do this in two ways, and I'm going to use math to show how I'm going to do that. So the first way we can use is calculus. I start by drawing a diagram of the cup, of the fluid at rest, accelerating through a distance, and then stopping after 1 foot. Here's how it looks like in slow motion. There's a certain point where the acceleration is the greatest, which means that this has the greatest incline. So I'm going to try to find the acceleration at this point. I know that velocity is distance per time, and I know that acceleration is velocity per time. I find that the maximum velocity occurs at 0.24 feet and 0.133 seconds, which gives me a velocity of about 2 feet per second. Dividing by time, I get about 14.6 feet per second squared. Now there's another method we can do to solve this problem. If I know this angle, there's an equation I can use to solve for the acceleration. Gravity times tangent of the angle. I found that the angle is about 30 degrees, which gives me an acceleration of about 18.5 feet per second squared. Although they should be technically the same, there are different errors in the experiment that lead to different results, but they are pretty close. Are you still with me so far? I hope you've learned something. If you don't understand the math, just at least think about this. It's pretty crazy how even just a simple cup of water can have so much physics behind it. Again, if you don't understand, don't worry. Just focus on making it fun. We can analyze a single point using equations, and that way we can derive the equation I've used. Consider a block of fluid made out of water. I'm going to use a diagram to represent this. So here we have this diagram to represent a block of fluid. There's pressure acting along the different x, y, and z axes, pressure, as well as gravity. But let's say there's a force acting along this. We can use Newton's second law, F equals ma, to analyze this. In the z, or up and down direction, if we use F equals ma, we have all these terms. Pressure going up minus pressure going down minus the force of gravity. Using different facts such as density equals mass over volume, and volume represented as x, y, z, plug and chug, and doing some algebraic and even some calculus manipulation, we can continue with this equation. The force of gravity, however, has a sign term because of the angle that it's at. Yeah, so you replace everything, cancel out x, y, z. I know it looks messy, but if you really want to know it, I'm sure you can do it. And moving stuff over, and eventually you get to dp dz equals rho g sine theta plus d squared z over dt squared. Okay, so this is the general form of the equation that we can use to solve the problem of the moving block of fluid. So as it moves, it creates a difference in height. Consider this point A and point B along an incline of an angle theta. The pressure at A should be the same as the pressure at B because it's outside and that's the atmospheric pressure. But there's a point C that's different. Using this equation, we can expand it from the y and the x directions. So for instance, for y, it's going to be dp dy, rho g sine theta, d squared z dt squared. And the angle is a 90-degree angle. Doing some algebra, you get that the pressure is equal to rho g h, or rho g delta y. Now from the x direction, using the same equation, now theta is actually 0, and sine of 0 is of course 0. So now you get rho a times delta x. But this pressure is the same, so we can equate these two equations, and let them equal to each other, cancel out the rows. By the way, rows density, sorry, didn't say that. And then using some geometry, you get the final equation that we use to solve for in the experiment. Okay, did you follow any of that? If you did, that's good. Good for you. If not, that's okay. I like to do experiments to make physics and science a little more fun, so hopefully you've had a little fun today. I've done a couple of these projects, so you can check out my channel for other videos like these, or you can leave a recommendation for what you might want to see. Maybe I'll do some more engineering videos and give some tips. Best tip is to get one of these multicolored pens and subscribe to my channel. Yeah.